Okay, in this video, we're going to go ahead and look at example 2 for the two-dimensional problems. We have a block that's being pushed across the table at a constant velocity. Solve for the normal force and the coefficient of friction in terms of the mass, the acceleration due to gravity, and the force on the block by the person. Even though this has the vector sign here, what I'm going to do is I'm going to go ahead and get rid of the direction for that. So let's go ahead and make that a scalar quantity that we're going to substitute in. Okay, so the first step is for us to draw our motion diagram. Since we're moving at a constant velocity, we're going to go ahead and draw our velocity vector the same length. Oops. Okay. Okay, so there's my velocity. My acceleration is going to be constant because I am not accelerating, so it's going to be 0. Okay, so now let's go ahead and ask ourselves, what's physically touching the block and what's acting at a distance? We have a block being pushed across the table at a constant velocity. So that tells me that I'm on a table. And anything else physically touching? The person's pushing it. Now, how is the table touching? Is it supporting, rubbing, or both? It's both. We do have friction. Okay, so we always have that support force, but really we're asking ourselves, do we have a frictional force as well? Okay, so we have that. We have the person, we have the table rubbing, we have the table supporting. What's acting at a distance? The Earth. Are we in equilibrium? Yes, we are. Okay, so we're going to draw our dot that represents our object. I'm going to go ahead and draw my weight and normal force. And then I'm going to draw my applied force and my frictional force. Now, if you're wondering why these two are equal, in other words, why isn't the force the person's pushing with greater? Remember that we don't want this force to be greater because we're in equilibrium. All the forces have to add up to 0. So this is force on block by Earth. This is force on block by person. This is force on block by table. And this is lowercase force, this is your frictional force, force on block by table. Okay, so now we're ready to sum the forces. We're going to go ahead and fold our paper in half. Okay, so I have the sum of the forces in X is equal to MAX. And I have the sum of the forces in Y is equal to MAY. I'm going to go ahead and add up all the forces acting in the X direction first. So I have F on block by table plus the force on the block by the person, and that's equal to MA sub X. Am I accelerating in the X direction? No, I'm not. I'm in equilibrium. So I'm going to put a 0 and put Newton's first law. Now I'm ready to substitute in magnitude and direction. So I have minus mu sub K, capital F on block by table. Again, remember, lowercase f, this is friction. Capital F, this is the normal force, magnitude times the coefficient of friction. And that's going to be in the I hat direction. Plus force on block by person, I hat, and that's equal to 0 newtons I hat. Okay, so the I-hats cancel out. And now I'm ready to solve for the force on, let's see, what are we solving for? We're solving for the coefficient of friction, and the normal force. Well, I don't have the normal force yet. So I'm going to leave this as it is because I have two unknowns. I don't know what the coefficient of friction is, and I don't know what the normal force magnitude is. So let's go over to the y direction. So I'm going to add up my forces. I have force on block by table. This is a capital F, so this is the normal force. Okay, plus force on block by earth, and that's equal to ma sub y. Am I accelerating in the y direction? No, I'm not. I'm in equilibrium in the vertical directions. Notice there's no movement in the vertical direction. Okay, substituting in magnitude and direction, I have force on block by table, j hat minus capital M, g j hat is equal to 0 newtons j hat. The j hats cancel out. And I have to do that because if I'm going to substitute in the magnitude of the normal force over here, I can't have the j hats. The j hat is a direction. Okay, solving for the magnitude of the normal force, I have force on block by table is equal to mg. Now you may be saying, well, Dr. H, it's obvious that that's the case. And yes, it is. But when we get into more complicated problems, it's not so obvious. And so I want to make sure that I'm going through the steps every single time so that when you get to more complicated problems, you'll still be able to do it. Okay, so now I can substitute this in for the magnitude of the normal force here, and I end up with minus mu sub k times mg. I've replaced this with mg plus force on block by person is equal to 0. Now I can solve for the coefficient of friction. I'm going to take this over to the other side, and I have force on block by person is equal to mu capital Mg, mu sub k. I'm going to divide both sides by mg, and then mu sub k is equal to the force on block by person divided by mg. Notice no vector signs. Oh, sorry. Notice no vector signs, and that's because the coefficient of friction doesn't have a direction. It's a scalar number. Now here's another thing. What are the units for the coefficient of friction? Okay, here we have a Newton, and we're dividing that by a kilogram meter per second squared. What's the definition of a Newton? It's a kilogram meter per second squared. So what happens? The units cancel out. Mu sub k, the coefficient of friction, is a coefficient. It should not have any units. Okay? So now we have that. Let's write our normal force. Force on block by table is equal to mg j hat. Now be very careful about this because I'm asking you for the force, but they could very well ask you for the magnitude of the force. If they ask you for the magnitude, should you be putting a vector sign in a j hat? No, you don't. So be very careful about what you're being asked for. Do not assume that because every example I'm asking for a force, that's what I'm going to ask for on the test. You have to make sure that you understand the difference between solving for the magnitude and solving for the force. Okay? It's very important that you understand the difference between this line and this line. Okay, that concludes example number